The basic definitions: fixed parameter tractability. Our concerns are decision problems with two or more inputs. Thus, we will be considering languages as L, which is a subset equals to the product of sigma star and sigma star. We refer to such languages as parameterized languages. If xk is in a parameterized language L, we call k the parameter. Usually the parameter will be a positive integer, but it might be a graph or algebraic structure. However, in the interest of readability and with no loss of generality, we will usually identify the domain of the parameter as the natural numbers n, and hence consider languages L, which is a subset equals to the product of sigma star and n. For a fixed k, we call Lk equals to the set of tuple xk such that xk is in L, the kth slice of L. As we have seen in the introduction, our main idea is to study languages that are tractable by the size. As the reader will recall, being tractable by the slice meant that there is a constancy independent of k, such that for all k, membership of Lk can be determined in time big O of the size of x to the c. However, such parameterized tractability can occur in many different flavors of uniformity, and for the sharpest results, it seems important to delineate these flavors. Before we give some precise definitions, we invite the reader to consider the following examples. Example 2.1, vertex cover. Instance, the graph G equals to VE, parameter a positive integer k. Question, does G have a vertex cover of size less than or equals to k? A vertex cover of a graph G is a collection of vertices V prime of G, such that for all edges V1, V2 of G, either V1 is in capital V prime or V2 is in capital V prime. Example 2.2, graph genus. Instance, a graph G equals to VE, parameter a positive integer k. Question, does G have genus k? That is, can G be embedded with no edges crossing on the surface with k handles? Example 2.3, graph linking number. Instance, a graph G equals to VE, parameter a positive integer k. Question, can G be embedded into 3 space such that the maximum size of a collection of topologically linked disjoint cycles is bounded by k? In figure 2.1, we give some examples to illustrate the problems above. The fact that K6 has link number 1 is due to Sachs and Conway and Gordon. If we consider the classical versions of the problems above where k is not fixed, then they are all NP-hard. Each of the above problems exhibits some form of a parameterized tractability. In the next section, we will look at a simple technique called the method of bounded search trees that can solve vertex cover using a single algorithm gamma running in time 2 to the k times size of G for each k. Downey and Fellows and Langston introduced a method which allowed them to use the deep results of Robertson and Seymour to construct a single algorithm, phi, which accepts gk as input instances of graph genus, such that phi determines if G has genus k in time big O of the size of G to the cube. This has recently been improved by Mohar to big O of the size of G. Finally, Fellows and Langston used the Robertson-Seymour methods to prove that for each k, there is an algorithm, phi k, which runs in time big O of the size of G to the cube and which determines if the graph G has linking number k. We will look at the proofs of these results and the techniques used in Chapter 7. Notice the differences between the 3 varieties of fixed parameter tractability. They are all big O of the size of G to the C for some C slice-wise, but In example 2.1, we have a single non-algorithm which works for all k, and moreover, we can compute the constant and hence the exact running time for each k. In the definitions below, we refer to this behavior as strongly uniform fixed parameter tractability. In example 2.2, we still have a single algorithm phi for OK, but this time we have no way of computing the constant in the running time. We merely know that for each k, the running time of phi on input gk is big O of size of g to the third. This behavior is called uniform fixed parameter tractability. In example 2.3, all we know is the exponent of the running time for the algorithms. For each k, we have a different and unknown algorithm running in big O of size of g to the third with unknown constants. This behavior is called non-uniform fixed parameter tractability. Considerations such as the examples above naturally lead us to the definitions below. Definition 2.4, the fundamental definitions. Let A be a parameterized problem. One, we say that A is uniformly fixed parameter tractable if there is an algorithm phi, a constant c, and an arbitrary function f which maps from n to n such that A, the running time of phi of xk is at most f of k times size of x to the c. B, xk is in A if and only if phi of xk is equals to 1. 2. We say that A is strongly uniformly fixed parameter tractable if A is uniformly fixed parameter tractable via some phi and f such that f is recursive. 3. We say that A is non-uniformly fixed parameter tractable if there is a constant c, a function f which maps from n to n, and a collection of procedures. The set phi k such that k is in n such that for each k in n, and the running time of phi k of xk is f of k times the size of x to the c, and xk is in A if and only if phi k of xk is equals to 1. In chapter 19, we will prove that even on recursive languages, the above definitions generate distinct classes of parameterized languages. The diagonalization arguments used in chapter 19 construct artificial languages to provably separate the classes. At present, we are not aware of any natural problem that is provably, say, in the class problems, a class of problems that are uniformly but not strong uniformly fixed parameter tractable. We remark, however, that there are examples of natural problems such as graph linking number, which can at present only be classified as non-uniformly tractable. Nevertheless, in practice, it seems that the most important types of parameterized tractability are the two varieties of uniform tractability. Until chapter 7, the reader can assume that unless otherwise specified, fixed parameter tractability will mean uniform fixed parameter tractability and most probably strongly uniform fixed parameter tractability. We remark that most natural FPT problems which have been studied so far seem to exhibit a general migration toward strongly uniform tractability. That is, once a problem has been identified as FPT with more precise combinatorics, we eventually show the problem to be strongly uniformly FPT. One reason for this general process of improvement is that often the initial classification of the problem as FPT came from the application of some general result pertaining to a class of problems containing the one at hand. Later, more uniformly, together with better constants and algorithms, can be obtained after studying the particular combinatorics of the problem considered alone. It is a very interesting open question to find some natural examples of languages which are FPT but provably not strongly uniform FPT. It is very important that the reader realize that parameterized complexity is orthogonal to classical complexity. That is, the parameterized complexity of a problem can bear no relationship to the classical complexity of the problem. For instance, let L be any recursive language. Perhaps L is not even elementary recursive, and the time complexity for L might dwarf Ackermann's function. But consider the parameterized language L prime, which is the set of tuple XX such that X in L. Classically, L prime has the same complexity as L, but as a parameterized problem, L prime is in FPT with a constant time algorithm. Later, we will see examples where the parameterized versions are hard, but the classical versions are easy.